Hi, in today's video we're going to be talking about transforming an alcohol into a good leaving group. So you can use HBr or HI to do this, but it's generally not very desirable because these are strong mineral acids. Those reactions will often proceed via SN1 or SN2 chemistry depending on the alcohol, but let's focus on reagents that can do this in a selective manner and avoid any kind of strong mineral acid present. So the first reagent that we're going to look at is called thionyl chloride, or SOCl2. And when we do this in the presence of pyridine, we can get this alkyl halide from this alcohol. The other reagent is phosphorus tribromide, or PBr3, and that will transform an alcohol into a alkyl bromide. Keep in mind, alkyl bromides are better leaving groups, and so that's a nice type of functional group to be able to make. So one of the things I want to point out with these particular reactions is that if your starting alcohol happens to be chiral and there's a stereogenic carbon at the carbon-oxygen bond, you're going to observe an inversion of stereochemistry of this carbon-chlorine and carbon-bromine bond. So that means that these reactions are SN2 chemistry. So in the case of thionyl chloride, you have to use pyridine to get this SN2 chemistry to be used. So go ahead and make note cards using these reagents. And again, make 3 note cards similar to what we saw for the elimination reaction or the dehydration reaction with POCl3. Let's look at the mechanisms at how they work. And you're going to see some real similarities here. So I want you to really focus on the similarities. So in this case, let's look at thionyl chloride. So you have your alcohol and you have your other reagent, in this case thionyl chloride. So the oxygen of the alcohol is going to react with the electropositive sulfur, and it's going to kick off the chloride ion. So again, this looks a lot like our first step with phosphorus oxychloride. Now we will invoke that pyridine is in solution. It's going to act as a base, and it's going to deprotonate this oxygen that has a formal positive charge to give us this neutral molecule here, and we will lose pyridinium as the counter ion. Here, chloride can come in and act as a nucleophile because this whole top portion is a good leaving group. It's a good leaving group because you lose SO2, either as a gas or as a dissolved gas, and chloride, again, good leaving groups. It's important to recognize that, again, this is an SN2 reaction, so this is occurring over a single transition state, this particular step, and you are getting an inversion of the stereocenter from this oxygen-carbon bond. It's now an inverted chlorine-carbon bond. One of the things I want to point out about that is that this is how it's often shown in the books, but it's been recently shown that this mechanism likely occurs actually with another equivalent of pyridine that comes in and displaces a chloride to form this pyridinium species here. The chloride can again act as a nucleophile here, where this whole big thing here is the electrophile, and in this case you lose SO2 and pyridine as your leaving groups. This is still an SN2 mechanism, and so in reality the evidence for this happens to be more associated with pyridine than with the actual reaction products. You are welcome to use this as your reaction mechanism, this top one where the chloride just interacts directly with this species. But it's always nice to know that there is still some ambiguity in terms of exactly what's going on. This is something that's still being studied. So let's look at the other reaction and the other reaction mechanism. So in this case, we have, again, our alcohol, and we have a phosphorus. So the oxygen is going to react with phosphorus, and it's going to kick off the phosphorus-bromine bond. So it's going to kick off bromide. As a general rule, when you are forming an oxygen-phosphorus bond in a mechanism, that's a favorable process. So phosphorus is thought of as an oxophilic, or a molecule, an atom that likes oxygen, and or is more stable making bonds to oxygen. And so again, when you see a reaction mechanism where you're forming an oxygen-phosphorus bond, you're probably heading down the right path. So in this case, this whole top portion of the molecule is a good leaving group, and the bromide is going to come in and displace this leaving group to again give you an inversion of stereocenter. So I'll point out again that this is an SN2 process where you are inverting the carbon-oxygen bond to make a new carbon-bromine bond. If it happens that the starting alcohol is not a stereogenic carbon, that's okay. It's still occurring via an SN2 process, but you simply don't have evidence for that in your reaction product. Thank you for your time, and I look forward to seeing you next video.